Thanks, Sam. I will begin with a word of prayer. Heavenly Father, we thank you for this day. And Lord, I thank you for these students. And I just pray that you'd guide our work today, Lord. In your name I pray. Amen. So I want to talk a little bit more about Maxwell's equations and all that. So let's remember Maxwell's equations. What were they? So I'll be a little bit irresponsible and state them without dimensional constants. So like the divergence of the electric field is the charge density, not the spherical radius, unfortunately. Charge density. The curl of the magnetic field is equal to the current density plus the time derivative of the electric field as it happens. Usually, last time I wrote them with some dimensional multipliers, mu naughts and epsilon naughts and so forth. Then you got divergence. Divergence of the magnetic field is 0. And then you have the curl of the electric field is minus partial B, partial T. So these 4 partial differential equations are known as Maxwell's equations because Maxwell was the one who had the insight to add on this partial E, partial T term, which actually is very significant in the sense that it predicts radio waves and other things. One of the things, so in physics 232 here, right? You study some of this material, and one of the things you do. So I want to just talk about the potential formulation. All right, so so you can actually write the electric field, right, is minus the gradient of a voltage function. So V is voltage. All right. And the other thing you learn about if you study junior level physics is that the magnetic field is the curl of the so-called vector potential. Right. So, like in the magnetostatic or the electrostatic case, you can calculate the voltage at R by doing something like the integral from your origin, wherever that is, to R of E dot, oh, that's not what I want to say. Actually, I don't want to say this at all. I'm teaching 232 here. The point is you can construct these voltage function, and you can construct the magnetic potential from integrating the charge density and the current density. Now, this isn't quite right, though, because, I mean, these we study. If you have a junior level course in electromagnetics, you'll study both of these things, the electrostatic case and the magnetostatic case. But you notice something, that these can't quite be right. If you look at this equation, what does this say? What does this say? There should be some sort of what? These can't quite be all that there is to it, because if my magnetic field is given by the curl of A, right, then this should be what? Right? So, being that physics is kind, it allows you to do things like commute, derivatives. You can do that. So it seems like I'm missing a term, right? My electric field should also have plus partial A, partial T, and this is, I believe this is how it goes. It's been a little while. So this is so-called potential formulation of electricity, electromagnetics. You need to have a voltage, which is the charge per unit area, potential energy per unit charge due to the electric field. And you also get this vector potential, which describes how the magnetic field is generated. But here's the deal. I mean, this is basically the prescription is given the voltage and the magnetic potential, you can calculate the electric field and the magnetic field by the derivatives given over here, right? So I'm just trying to give you guys like just a kind of quick and dirty summary of a course in physics we don't offer. All right? This is what's beyond Physics 232 in terms of potential formulation. There's the magnetic potential, and then it actually goes together with the voltage to give you the full. This is what's needed in the case that you're not in the electrostatic case. You have charges moving around. Partial A, partial T accounts for that somehow. So here's the neat thing. If you look at A as being a one form in 4 dimensions, this one form being minus v dt. So I want a one form in 4 dimensions that's somehow related to the potential formulation of electromagnetism. What should I do? I mean, I take my scalar function, my voltage function multiplied by dt. There's part of it, but what do I do with the vector potential? How do I convert that to a one form? How about omega sub A, right? The work form corresponding to that. Now I got a one form, right? And what I want to show you is that the exterior derivative of this one form, this is the so-called one form potential, or potential one form. If we take the exterior derivative of this potential one form, then what we get is the defining derivative conditions over there. Let me show you how. So this dA is what? So I've got like minus dV wedge dt, right? Plus d omega A. Keep in mind, of course, that A and V could possibly have time dependence, right? In this context. Okay, but that doesn't matter here, because if V has a time dependence, partial V, partial T, wedge dt is still 0. So the only thing that actually comes up from this is what? The minus omega of the gradient of the voltage, wedge dt, right? And this guy, well, it's got the flux form of the curl of A, right? And then plus what? Plus, I'll write it out in detail again, plus dA1, sorry, but which terms have I neglected? I've neglected like partial A1, partial T dt, wedge dx, plus partial A2, partial T dt, wedge dy, plus partial A3, partial T dt, wedge dz. If my memory was better, I already had the formula on the board last time. I'm kind of working it out again. I'm sorry about that. Let's see here. So if we put all our stuff together, what we got? We got like we've got an omega, right, of minus the gradient of V, right? And if I put my t, oh man, see, I'm off by a sign. Son of a gun. Dang. think I'm off by a sign. You see what that is if I flippity floppity? This is minus partial a partial t. It's the work form of that wedged with dt. See, I have to that piece. Of course, plus the flux form. Now, what did I define the Faraday 2 form to be last time? What was it? We used a capital F, and we said it was, what was it? It was I said it was omega E. Go to sleep on me. It was omega E wedge dt plus the flux form of B. So it looks like I'm off by a sign. I think we can fix this. Unless I've made a mistake. Apparently I was supposed to do what? Not plus partial a partial t, but looks like I need a minus there. Right, if I put a minus there, then that then this is E, right? And this is B. And so this is F. So if I get my sign conventions right, we can fold the scalar potential and the vector potential into a single 4 potential whose exterior derivative gives me the Faraday 2 form. And then what's really beautiful here is, well, if you calculate df, right? On the one hand, that's equal to the d of omega E wedge dt, right? Plus the flux form of B. And we worked out that that gives you like the curl of E, right? And the divergence of B and stuff last time, right? But the fact that that's 0, why is that 0? Yeah, this is d of dA. So d squared is 0. So the Faraday tensor has to have an exterior derivative 0 because it is an exact form. It's the exterior derivative of the one potential. Let me not be fuzzy here. We worked that out exactly last time, so just leave it at last time we worked out. But this being 0, actually, explicit details say that it's these two, right? So these two Maxwell's equations are basically given by just saying dA is equal to F. Automatically follow from that, because that gives me that dF is 0. But the other thing that's really cool about this is you get to see what gauge freedom looks like. What if I took A and I made a new A, which was by the old A, plus the exterior derivative of any function you like of space and time, lambda. See, if I add the total derivative of any function of x, y, t, x, y, z, time space, well then, you notice what happens is that the exterior derivative of that is the same as the exterior derivative of my original potential. So apparently there's a lot of freedom in how we calculate A. We can add a total differential of a function of time and space to that. Right. So you can eliminate that freedom by setting what's called a gauge potential, making a gauge choice. There's various choices which are popular: Coulomb gauge or Lorentz gauge. But I'm kind of getting off topic a little bit. So one of the problems I like to give in this course is like, here's a voltage function, and here's a vector potential, find the Faraday 2 form. This is just kind of a cheesy, take an exterior derivative, take a couple wedge products question. But it has a profound physical significance, so I like it. The other thing I should say here, and then I will stop talking about this, is that this is the start of how we actually understand gauge theories in more generality. So roughly speaking, the way we do physics these days is you got something like M is your space-time manifold, right? And then you imagine attaching at each point in this over the space, you imagine sort of attaching some gauge group G. Think about attaching a gauge group G at each point in space-time. You can think about it kind of like that. But these gauge groups have to be attached in a way which respects special relativity, which respects the structure of space-time. Turns out that working out this carefully leads you to what's called a principal fiber bundle. A principal fiber bundle is something that's like a fiber bundle, like the tangent bundle, except the fiber over the principal fiber bundle is actually the gauge group. And how the gauge groups glue together over the manifold somehow encodes physics. So there are various gauge theories which we have experimentally observed. Of course, electricity and magnetism. Electricity and magnetism, you have G equals to U1, the unimodular group. So U1's 1 by n1 complex numbers, basically things of the form e to the I theta. It turns out that this is the gauge group that underlies electricity and magnetism. But if you go on and you replace that gauge group with something like SU2, this is what gives you what's called Yang-Mills theory. Yang and Mills discovered this in the early mid-50s. Japanese by the name of Uriyama did it for an arbitrary, essentially arbitrary gauge group. And through much the same mathematics we're doing right here, you end up discovering generalizations of Maxwell's equations derive naturally from what's called a connection on these principal fiber bundles. But those, so what I'm starting to describe to you is what's known as Yang-Mills theory. And so what Yang-Mills theory is basically electricity and magnetism when you replace the U1 of E and M with some matrix group, for the most part, what people do. It's like SU2 or SU3, special unitary or special unitary 3 by 3. SU2 gauge theory describes, for example, radioactive decay. The weak and electric forces. Actually, so there's something called symmetry breaking. If you go up higher in energy, there's some combination of electricity and magnetism and the weak force called electroweak. And so that's an SU2 theory. And then some of that splits with this symmetry breaking, and there's this Higgs boson floating around and giving mass to things. It's a complicated, long story, but most of it has been experimentally seen at this point. And this physics discovered 1950, 1970, something like that, a lot of it. Although experimentally, we only found the Higgs, I don't know, 5 years ago, something like that, not long ago. SU3, that would be QCD, quantum chromodynamics. That's the the gauge force behind like the color, like the interactions between quarks. That is still a little bit more out there, but there's a lot of experiments to do that too. And you can even view general relativity as a principle, as a gauge theory. Feynman wrote a book on this, for example. But anyway, this notion of gauge theory, this idea of attaching a group to space-time in some way which is local, which respects the structure of locality in physics, this is generally what we think of as gauge theory. So, now here's something that will really mess with your mind. In the early 1980s, we realized that you could use this kind of physics to do topology. And that we does not include me. I was 2 when this stuff was done, but this Donaldson and his Donaldson invariants, we discovered all kinds of new exotic 4-dimensional manifolds by exploiting analogies with the physics of instantons. And then that later gave way to the Seiberg-Witten things, which I do not understand, but apparently is a calculationally lucid way to get at the same stuff Donaldson got at. But anyway, thousands of pages have been written on this in the last 10 years. It's still very much underway. It's fascinating to me, though, that this interplay between physics and topology continues to be productive, even these many years after Poincare. All right, I think I've digressed enough for one day. Let's get back to the McNerney. So I really like what we're going over today. I think it's really understandable. And as long as I don't get sucked into doing certain proofs, we'll all be happier for today. I mean, every proof which is tough to understand in the sections I'm trying to talk to you about today, it's the chain rule. It's just the chain rule run through the notation. Don't be scared of them. It's just the chain rule. But, you know, that's really not much consolation. I think the chain rule is probably the hardest topic in calculus to understand in abstraction. To really understand the chain rule is to understand calculus. Of course, I ignore integral calculus because it's convenient for my current discussion. All right. Sorry. Had to get that out of my system. By the way, if you want to read more about Yang-Mills theory and just generally quantum mechanics over a more general sense, this Anomalies in Quantum Field Theory by Reinhold Bertelsmann is a great place not to start, but to finish. Like, after a few other books you read, you should look at this, but it is a great book. All of my friends who went into string theory spent countless hours in that book. All right, so tensors, section 4.6. So it's about high time I gave you some terminology here. So a tensor of type, so here's the main thing I'm finally fessing up to, type RS on V it's a mapping from R copies of the dual space and S copies of V to the reals, because we look at real valued tensors. You could replace that R with something else, but then it would be a whatever valued tensor. R of these, S of those. And he says that TRSV is the set of all such things. Just multilinear. That's what it takes. We say T is an element of TR comma S V. All right. People used to say it had rank RS. I think that's bad terminology because the term rank has a meaning in linear algebra, and we don't want to because that actually becomes, those I think are open questions in abstract linear algebra or abstract matrix theory. Calculating the rank of a tensor in the linear algebraic sense can be a very difficult and sometimes open problem. All right? Just saying. So we should say type RS is all I'm saying. Okay, if we say type RS, then we're out of trouble. Now, so these you can build. It's essentially the span of these guys. So what you need to eat dual vectors, we can let standard basis vector eat dual vectors according to our usual notion. I'll explain in just a second. Forget if we've talked about this already. So this is naturally a mapping from V cross the dual a bunch of times, and the V to the reals. Where we've got 1 less than or equal to I1, IR, J1, JS less than or equal to N. So just all possible indices. Let me give you an example. If we have E1, tensor E2, tensor E upper 3, all right, this would be a type, looks like to me, type 2, 1 tensor. So a type 2, 1 tensor, we feed it. What does it eat? What do you feed it opposite data, essentially. So you feed this a 1 form, another 1 form, and a vector. And how is that defined? It's defined as follows. That's alpha acting on E1, beta acting on E2, and then E3 acting on V. Audrey looks moderately unpleased.
I think it's because of the type that the different things are, why the things act on them and that.
Right. So since alpha and beta,
Those are forms, they do a different thing.
yeah, these are mappings from V to the reals. So if I want to produce a number from that, I let alpha and beta act.
You can't feed them 2 things because that won't make a number.
Right.
That will make something.
Right. So, and then in terms of our lemmas from the other day, this is actually alpha 1, beta 1, V3 for what it's worth. Okay. It actually picks out the first component of alpha, second component of beta, and the third component of V for what it's worth. If you use the 2 fundamental lemmas we put on the sideboard over here that day. Good. Well, that's what I want. So, of course, these are not actually what we're interested in. We're actually interested in tensor fields of type RS. So the fundamental building block for those. So let me just write a Glenn. Here's a horrible but general formula for one. Some I1 through my eyes are going I through IR, and because my sum was too small, I'll make another one. Some J1 through JS. These are going over all things because, let's see here, there. And then T, let's see here. So I want I1, I2, IR. And you know what? McNerney has just put the indices for the other part underneath these. That's not a good practice. It pays off in the end to keep these over here. When we get to the next chapter, at some point it pays off to not put them over each other, to like, there's R plus S slots for the components, and let's just keep them like this. That's going to work out better for us in the long run. You'll see why. And so then this is just a function, actually, and that is getting, that's partial xi1 tensor, partial xi2 tensor, tensor. Oh, wait a minute, have I? No, I did it right. Partial xir, tensor dxj1, tensor tensor dxjs. This is what a tensor field looks like over a manifold which has coordinates x1 through xn. Now, I say manifold, but honestly, we're going to be working in Rn, so, you know, mostly it's just these are coordinates on Rn. Now, a tensor is a smooth, we attach one of these, a tensor of type Rs, smoothly at each point. That's what a tensor field is. So these are not numbers anymore. These are actually smooth functions on M. Right. And I can be more specific. In fact, what are they? They are what you get from feeding T, the corresponding these guys. For what it's worth, that's actually how you calculate the components. You just feed it the same, well, the dual thing. All right. Don't worry. We're for the most part, do not fret. I mean, I'm trying to just put the general thing out there, but by and large, we just work with either dual vectors, vector fields, or differential forms, right? So like a differential form, a special case, of course, well, one form fields are what? These are type what? Vector fields are type what? K-form fields are type what? So one forms just take in a copy of V and map it to the reals. These V duals aren't even present. So it's a type 0s, 0, 1. The vector fields, you can kind of see from just looking at this formulation right here. How would you get a vector field? Is like if you just had what? Everything gone, except for this first thing, right? So vector field's the dual, it's type 1, 0. A K-form is a particular type of 0K tensor. So we have this, that lambda K of M is a subset. It's really a subspace, although this is not a vector space, it's something else. It's a subset of the tensors of type 0K over M. Although he never, if you read McNerney carefully, as far as I can see, he never actually gives a name to the set of tensor fields. He just will say, it's a type RS tensor over this thing. All right, so he actually dodges the problem of inventing a name for the set of tensor fields. I'm being glib and just saying, why don't we call it that? But that's, well, anyway. Admittedly, that is at odds with our other notation, which is why he probably doesn't write it. Okay, so pullbacks. How can we pull back a tensor field? So if you've got U, all right, and then over here you got V. These are both subsets. So he has phi going this way, all right? And then he has psi going that way. Psi is equal to phi inverse. So it turns out if we have a diffeomorphism, we can talk about the pullback of a tensor field. And here it is. So I don't even want to write down, because I think I'm losing you guys. Let me just, if you'll allow me to skip the preamble to it and just write the main formula here. The pullback of the tensor field S, all right, what it's going to be under phi, when it acts on alpha 1 through alpha r, and then vector fields x1 through xs. You do what you got to do. You let S, so here's the way to think of it in the picture, is S is a type RS tensor on V. S is over here, so to speak. All right, and over here we're going to pull back S. So I guess my language would be that S is an element of the tensors of type RS on V, whereas the pullback of S would be a tensor of type RS on U. We're assuming here that phi is a diffeomorphism, which is what? It's a smooth map with a smooth inverse, right? Okay, so if you guys just think about this, you can tell me what to do. How do I get, I mean, these alpha, these are what? These are one forms on where? On V. These are vector fields on V. But I need to feed S what? I need to feed S. I need to feed the pull. I'm sorry, I'm an idiot. U. I'm a stooge. Grief. This is supposed to be, I'm pulling it back over to here, right? So this is the data on U that I'm feeding it. Idiot. All right. So how do I take that? What do I do? Push forward the vector fields, right? The forms, I need to pull them back from, yeah, U psi. So pull back, so psi, pull back alpha 1, psi, pull back all the way over to alpha r, and then I just push forward the vector fields. Yeah, push them over here. Great. So I use phi for that, right? So somewhat, I think you were asking me about this after class, Sam, weren't you? Like, you were asking about the duality between push forwards and pullbacks. Like, this is kind of the end of your discussion. I mean, it's, so we did. In the presence of diffeomorphism, we can have both. We can have our cake and eat it too. I mean, we can pull our cake and push it too, or I don't know. I mean, whatever you want to call this thing. In the presence of a diffeomorphism, we can take data from one side of the map and put it to the other, and vice versa. We can push it back and pull it forward. There's also something, obviously, you could also define the push forward of a tensor much the same way, right? Professors are right. What?
I don't think you would say something that simple if it were false.
Oh, yeah. I just think it's not a trap. I just think it's fairly. There's lots of toys to play with here. I mean, you can use either phi or psi to either pull things one place or push them to the other, and you can do it both ways because there's a complete symmetry between the u and the v here in the presence of the diffeomorphism. Okay. This is important because the definition of Lie derivative, it's all about this idea, really. Let's see here. Let me just, without even giving you the details of the calculation, let me just tell you. He has two examples of this, which are probably worth just writing down. I won't belabor them. I don't think they're that interesting, but maybe they're worth a minute. So his example, and the details are, well, the chain rule. Example 4.6.13, he looks at the tensor dyj, all right? And he's looking at phi being a mapping from Rn to Rn, all right? And so where his notation is that phi of x1 through xn is equal to y1 through yn. Anyway, so the pullback under phi of this tensor, dy, acting on x, you work it out, and what it actually is, let me just write down what t is. The pullback of dyj acting on x is equal to x acting on yj. And he has another example. I'm not even going to write it down. I don't think it's particularly enlightening for our current discussion. I'm going to go on. Got to know when to hold them, when to fold them.
Could you at least give me a number of it?
Yeah, it's the next one. It's 4.6.14. He basically just pulls back. Instead of pulling back the one form, he pulls back the fundamental vector field. Yeah.
Thanks.
Uh-oh.
Is there, I mean,
Sweet.
I just wondering, is there a push forward of the tensor? You pull back and you push forward.
Yeah, I think so. I think that the push forward, you could.
Is the push forward is the inverse of the pullback of the side? And there's some. The push forward.
Yeah, I think in this way of thinking, it seems legitimate that under diffeomorphism we could push the tensor forward, and then we could pull it back with this idea, and we'd get back to the same tensor. I think that's not wrong. The central thing being that you'd end up with something along the lines of, I think when you actually sorted through it, you'd end up with stuff like this, which would then be this, which would then be this, which would then, yeah. But anyway, yeah. You know, that sounds like it'd make a really interesting homework problem. Let's see here. Okay, so properties. Well, Audrey has guilted me into writing the answer for 4.64. Audrey, pull back of partial yj in this way of thinking. You're fine, Audrey. I'm just messing with you. Alpha is actually equal to alpha of the how does this even write this? I feel like my star is supposed to be down. Here, seems like it's probably that. Again, I don't think this is that interesting. I'm moving on. I should have stuck with my original. There are calculations which you will understand, which will be mutually productive. Here, let's go on. Proposition. I mean, the whole point of those examples is to illustrate the definition. So if it's getting in the way of understanding the definition, then they're not productive. And there are ways that the definition is illustrated later in the next section, which are far more interesting. So let's get to those. So, but I must be a good citizen of the mathematical world and write a few things here. This assignment, where the assignment is this: we take the pair of tensors ST and we map it to S tensor T in the pointwise fashion. So that's point number one. And can you complete the thought for me? What's missing at number one? There's a number of theorems like this in this section and the next in McNerney. The punchline there is that that assignment is bilinear. That's number one. Is if you take a pair of tensors of type RS and another tensor of type KL, and you take the tensor product of those together, then you get a tensor of type R plus K, comma S plus L.
So those are different S's.
Oh, what have I done? These are big S's. You put some. There we go. Is that better? Yeah, but the T, I mean, come on. Yeah. There we go. Now, this brings us to the definition, which would have probably been helpful. Now, I'm at least one of you has finished your homework, but I know many of you are still working on it. I'm happy to take it Friday. And that's, yeah, no, it's fine. You know, I cover a lot of material in here. Some of it's hard and it takes time. I know, it's fine. Let T be a 0K tensor. All right. I mean, it's okay. And let X be smooth operator, I mean vector field, but for us the same thing, right? Smooth vector field, then the interior product, finally, the interior product, it has a seat at the table because today it cannot be avoided. I have skipped the discussion of it in the linear algebraic sense of it in an earlier section, but now we're actually using it to do things, so I feel like I'll talk about it today. Interior product of T and X is denoted So he does I, X, T. All right, and this is a 0, comma, k minus 1 tensor field. All right, and how you do it? I of X acting on T, it acts on Y1, Y2, Y k minus 1. Here's your smooth vector fields. All right, and what happens? Get T of X, Y1, Y2, Yk minus 1. You're like, this needs a name? Yes, yes, this needs a name. Because it's actually an important operation. This is the coordinate-free version of a contraction. So contraction is, in physics, one of the principal methods we use to construct scalars, things that are invariant under coordinate change. If you have a contravariant and a covariant indice and they're summed over one against the other, when you do a coordinate change, the contravariant and the covariant indices, they transform inversely. And so what that means is that if you can write down something from physical variables that's a scalar, that's a contraction of a covariant and contravariant index, you've got something that might have physical meaning because it's independent of the coordinate system which is used to create it. This is the algebratization of that, this contraction idea. And what he goes on to say in this section basically shows that it respects, it's not even a word, respects, what's that? It respects the, goodness gracious, the C infinity smooth function module structure. In fact, tensor fields are a module. Like, what's a module? A module is like a vector space, except the scalars are not a field. They're a ring. And in this case, the ring that we're dealing with is smooth functions over the manifold. So if you look at the rest of the propositions in this section as they relate to this interior product, they're all about the module structure of vector fields or the module structure of tensor fields. The fact that you can take a smooth function and multiply it by an RS tensor field, and you still get an RS tensor field. And the propositions which follow for this say you can pull smooth functions out of the interior product. That's what it's needed for them to be a natural map that respects the module structure, this multiplication by a smooth function. Anyway, this is sort of danced around in this section. It's never said explicitly, and that's fine because it probably shouldn't be. Sorry. There it is. Oh, by the way, another notation for this is X hook T. The hook by X. This is popular notation in the applications of differential geometry to mechanics. It's like people do classical mechanics in the abstract way. They will work with this hook product a lot. It comes up in the Hamiltonian mechanics. All right, so examples. I love his examples for this. They're fun. These I think you guys will understand, and they won't make you tired. So he lets G equal dx1, tensor dx1. He doesn't care about indices up or down, except when he does. I guess it's just like me, isn't he? Let's see here, dx2 wedged, not wedges, tensors. All right. So this is a type 02. In fact, it's a type 02 symmetric tensor. I should give you guys homework about symmetric versus antisymmetric tensors, shouldn't I? Let's see here. Oh well. And he looks at X, the vector field. He looks at it is partial F, partial x1, partial x1, plus partial F, partial x2, partial x2. What is this? This is, you should recognize this. This is the gradient vector field of f, isn't it? So what is like, here's a tensor, type 0, 2. Here's a vector field. Let's calculate the hook. I'm sorry, the interior product of x with g. All right? And I think to do that, he also feeds it a y. So ix g of y. So how does that work? Here, that's just g of xy. But what is that? That's dx1 of x, dx1 of y, plus dx2 of x, dx2 of y, right? Because that's how the tensor works, right? When you feed a pair to these, they eat the entries like that. But dx1, sadness. This gives me the first component of x. This gives me the first component of y. This gives me the second component of x. This gives me the second component of y. This is a what, by the way? This g, what is it? G is the dot product, yeah. But anyway. But more specifically here, with respect to this x and this y, what is x1? x1 is, this is my x1, right? And let me use a different color for that. So my x1 here is partial f partial x1. This is my x2, right? So I've got partial f partial x1 of y1 plus partial f partial x2 of y2, which if you tilt your head and squint, you can see that that's actually partial f partial x1 partial x1 plus partial f partial x2 partial x2 of y1 partial, oh, I'm sorry, I can't do math. Curses. Oh, I'm sorry. My brain just left me in the, no. It's not helpful. Stop that. What is this? I mean, you could say, okay, well, that's the answer. I mean, that wouldn't be wrong. But there's something slicker to say here. Oh, I lost it over here. So this is really partial f partial x1 dx1, right, acting on y, plus partial f partial x2 dx2 acting on y, right? Because remember, we can use the dual basis to select components, right? And so this is nothing more than df acting on y. So let me go a step further. Then the book doesn't even mention this here, but you notice from this, because y is arbitrary, we actually have this. Let me go a step further. This is the musical morphism I was talking about. What's happened here? What just happened?